Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to our NPTEL online certification courses on engineering drawing and computer graphics. We are in module number 7 learning about how to construct surface models, and for that we are learning little bit about overview on computer graphics. So, in today's class we will learn about various surface construction techniques. In all these surface construction techniques, we mainly use cubic polynomials as the basis functions. For example, we have a data points something like u1, u2, u3 and so on, and if we want to, if we are interested in constructing a curve first, then we will impose that it satisfies a cubic relation, where C naught, C1, C2, C3 are the coefficients and u is a parameter which we might be in a position to say it like what are the x, y, z coordinates, different x, y, z coordinates we are going to plug it. So, that we will be in a position to get a parametric curve. Here each of these C's, C naught, C1, C2, C3 basically represents the weight functions of that polynomial curve. They can be 1 kind of thing, or 1 0 kind of thing, 1.5 0.1 that kind of thing. So, these weights we carefully tune it so that a nice curve really pass through these points. Once we construct these cubic polynomials, then we will interpolate, apply the same technique to construct the surfaces. The first one, in terms of Hermite bicubic surfaces, what we do is we construct a curve between points. Those points, if we are joining, if we are getting a specialized curve, for example, the point P naught, P1 we know, these are any x, y coordinates of that system. We have information about that point, we have information about P1. And similarly, we have information about the tangent at P naught, which we are representing P naught prime. Similarly, the tangent at P1, which we are calling P1 prime. If we have this information, a curve in the direction, if we can interpolate based on those tangent informations and point information, a smooth curve, if we are passing through that, we call that as Hermite curves. They satisfy one particular relation where your P, any point P on that curve, supposed to satisfy this relation. Hermite curve which we are trying to look at even on the surface. So, you pick any Hermite curve which is passing on that surface, pick that point where u v information we have parametric variation. On that surface, the point in the direction of u v supposed to satisfy this relation based on the points and the tangent information what we have. And when we are constructing that, we try to minimize certain issues like weights and other thing. For that purpose, we try to use the function values, and also their derivatives, try to impose at different points to get that surface. And that matrix, based on how smooth that is, how regularly it is conditioned or ill conditioned, based on that we will be going to construct these surfaces. There are other ways of constructing surfaces also, those are called Bezier curves and Bezier surfaces. In that, we have particular data points like P1, P2, P3, P4. We do not straight away join these data points. What we do is, we construct based on certain polygons fit in between these data points. And when we are fitting these polygons, whatever the curve which pass through that crossing these polygons, that is what we call Bezier curves. If I am representing it in terms of parametric variation, the P, any point P on that curve, the parametric curve, supposed to be expanded in terms of Pi, Ki, where K1, K2, K3, K4s have these cubic interpolations. So, T is our parametric variable like our U, a cubic polynomial, a cubic, a cubic, a cubic in different kind of formats. We are going to carefully adjust so that we will be in a position to construct a polygons through which this particular polynomial curve really passes. If we are going to do that, that kind of curves what we call as Bezier curves, and these are the most popular representation curves. And when we are drawing such kind of curves, we require only 4 points to construct that smooth curve. For example, we have point P1, P2, P3, P4. One way of representing this one is, maybe I will be just going to construct like a line, or perhaps I just construct something like a spline. The best representation is to go with this Bezier representation, where by minimizing these weights, we will be in a position to construct a curve. Most of the graphics editors, the softwares whatever we are going to really draw the curves and render the things, works on these Bezier curves. If we are looking that in 3 dimensions, for example, this is the first data, these are the 4 data points we have. Then first we will construct a Bezier curve in that. Similarly, we will be having other data points like 1, perhaps 2, at bottom 3 and 4. Then again we will be in a position to pass another Bezier curve. Similarly, another Bezier curve, another Bezier curve. Similarly, on the other directions we have 4 data points. So, pass a surface, a Bezier curve in that way. So, that we will be in a position to construct a free surface on that object. By just knowing 16 data points, we will be in a position to construct a very smooth surface. Let us look at carefully. The data points what we have is 1, 2, 3, 4. Similarly, 1, maybe 2, 3, 4, a bottom 5 and so on. These are the data points what we have. Now, one has to construct a surface because these data points are scattered. What is the best way one can really have that surface? For that purpose, what we require is, if we have minimum 16 points, by using these Bezier curves principles, one can construct this one, a smooth surface. As with the surfaces, the curve itself does not exist until we compute combining these 4 points weighted by some coefficients. So, what is that curve does not exist? What we have these discrete data points. From there we are trying to construct it. The other way of representing these data points trying to construct surfaces is called B-splines, which is also called as basis splines technique. because it is a drawing course, we are not going too many details into mathematical formulation of these curves, but just to have overall idea about what kind of curves are good for what kind of applications. That is the thing what we are going to learn about it. In basis spline techniques, we are going to use polygons instead of any cubic polynomials. So, instead of using any cubic polynomials, if we are going to have these polygons, we call that as basis splines. The term B-spline was coined by Isaac Jacob Schoenberg and is a short representation of saying basis spline. A spline function of order n is a piecewise polynomial function of degree n minus 1 in a variable index x. The places where the pieces meet are known as knots. The key property of spline functions is that they and their derivatives may be continuous depending on the multiplicity of knots. How complicated these knots? We might be having smooth curves. And we do not use anything like cubic polynomials like what we have used for Bezier curves, but here we use polygons. By carefully adjusting these polygons, we will be in a position to construct surface. For example, we have these data points. The easiest polygon what I can really fix is something like a tail, a rectangular tail I can put, maybe a rhombus I can really construct, or perhaps a triangle I can really construct. So, varying these kind of objects, I will be in a position to construct a surface. So, based on controlling those polygons, it can be hexagon, dodecahedrons and so on things, we will be in a position to construct a nice surface. B-splines of order n, basis functions for spline functions for the same order defined over same knots, meaning that all possible spline function can be built from a linear combinations of B-splines. The advantage is you can really add it up as a linear function, that is the advantage what we will get with these B-splines. And there is only one unique combination for each spline function. When you are using that, there will not be any multiplicities involved in that surface construction. You will be having that unique representation. For example, like ship hulls you want to construct and so on, usually these B-spline surfaces are quite popular. If you open any CAD software, maybe SolidWorks, AutoCAD, these options you will be having, or OpenGL, these kind of softwares where you will have this kind of options, like whether you would like to really interpolate it like through B-splines or Bezier curves or Hermite basis functions and so on. The other kind of representation is by Gordon surfaces. So, this kind of Gordon surface is called free form surface molding. That means, you have data points, you can really drag drop so that surface is naturally adjusted on that CAD software. So, you will be having a network of G1, G2 curves. For example, like if I am saying something like this is one curve, you have another curve, you have another curve, and you have isolated data points here and there. Now, using your CAD software, you can just pick one of the data point, move your mouse here and there, so that surface variations you start seeing. And you carefully pull your surface in all these points, nicely mapped to get a smooth kind of surface. That kind of surfaces what we call Gordon surfaces. It satisfies certain kind of relations like your G1 curve, G2 curves, and the intersection of these G1, G2 curves supposed to satisfy certain blending functions. For example, like you have drastic variation on these surfaces, like you are making a automobile engine cylinder where mufflers will be there, sudden change in this pipeline structures will be there. Then the easiest way what you can really construct is these Gordon surfaces. Here such kind of object is shown. Something like a cylindrical nice surface comes, suddenly there is a bump happens there, a kind of dent also there. So, you would like to really fit a nice curve through that, or perhaps you are working on biomedical field, you have femurs or bone structures. These are not just described by very smooth curves, there might be sudden variation happens on these bones. You want to really reconstruct such kind of objects, then the best way of looking at that is using these Gordon surfaces. It is not necessary that the hip bone joint kind of thing might be circular, it might be having some specialized curve. So, when you are actually taking pictures through cameras, you will be having isolated data points. Now, you want to reconstruct it and transfer that entire data to your 3D printing object. Then what you do is you use those pixel informations, try to construct these Gordon surfaces and teach it to the computer or to that machine element, print it in this way. For that purpose, these kind of Gordon surfaces will be used. Especially for jet engine ducts and other things where sudden abruption happens, you use these Gordon surfaces. The other kind of surfaces are Coons surfaces. Especially the B-splines, the basis splines are popular when boundaries are open. You have discrete data points, but these discrete data points are not forming any boundary. Somewhere inside of that object you have it, then you use B-splines. But if these data points on one particular kind of boundary, we employ these Coons surfaces, and these Coons surfaces are better approximations. So, Coons is a famous pioneer in the field of computer graphics. He was a professor at MIT and he has spent a lot of time in terms of constructing these design tools for engineers. So, something like here in an abstract sense, we have this curve or the data points on that particular curve and those forming boundaries. What is the best way of constructing these data points or surface inside of that, which we do not have any information. What we have is only the boundary informations we have. What is the best way I can really construct that surface? It looks for visual very nice, but construction means it requires a little bit mathematical skill set. So, any CAD software actually employs that background programming to construct such kind of surfaces. A Coons patch is a type of manifold parameterization used in computer graphics to smoothly join other surfaces together, and in computational mechanics applications, particularly in finite element methods and boundary element methods, you would like to really mesh the problems of domains into elements and so on. These Coons surfaces are quite popular. So, there are certain mathematical procedures to solve differential equations to understand the fields, which we call finite element methods. You have boundary conditions on one of these particular things, and maybe a surface you would like to really represent a smooth surface, then you employ this Coons surface. Even meshing, maybe locally zooming into that picture, these Coons surfaces always be helpful. And further on these Coons surfaces, people try to use a blending, try to smoothen these surfaces, and even if you are zooming, that pixel variation should not really vary. That kind of techniques what people use. For that they use bilinear and bicubic kind of interpolations also. So, here what we are seeing is basically the engine duct. The aeroplanes, the jet engines what you have on the wings, you will have something like jet engines which grab air, put fuel, burn it, so that exhaust will come out, and that can supply the thrust of that engine. So, these ducts always have some specialized kind of form. If you are looking at that, they nicely turn and twist in that directions. For that kind of surface construction, these cone surfaces are quite popular. So, other than that, when you have these curves, edges, we do not want to really have very sharp things. Making these sharp edges always be bit difficult also, we want to round it off. Such kind of thing if we are going to do, we call fillet of that surfaces. For example, we have a plate, a rectangular plate, and again we want to join by another one. We have these sharp corners, we do not want the sharp corners. What we do is, we try to remove that surface, make it something like smooth. For example, here that rectangular portion, we have a smooth corners. Because the sharp corners we try to avoid it, because it might affect our productivity or harm, or perhaps scratches forms, or it is difficult to maintain the surface particular thing. So, we always round it off. Such kind of things what we call fillet surfaces. A fillet surface is a rounded corner connecting the edges of two other surfaces. The easiest way is, you pick a radius of curvature, a center, from there you draw an arc to join as a tangent to this curve and remove the remaining material and extrude that information, so that you get a fillet surface. Here we have another kind of representation. You have this rectangular plate, you try to construct this smooth surface and try to add to these portions. That is what we call fillet surface. Similarly, let us look at this. Maybe you have an automobile car, windshields have to be nicely aligned with the object. It should not be sharp variation. For that purpose also, we use fillet surfaces. Whenever you are going to use these fillet surfaces, the popular way of using is B-spline surfaces, one can really use it. They will be nicely mapped from one point to other point. Similarly, at CAD software, we use other variety of surfaces named offset surfaces. You have one surface, with respect to that one surface, with an offset, similar kind of surface we would like to construct it. For example, I have a cylinder, for example, I have a cylinder. I would like to have one more concentric cylinder around that. If I am going to construct such kind of thing, that is what we call this offset surfaces. Here we have some asbestos kind of sheet, the roof. A parallel thing we would like to construct, that is what we call offset surfaces. Here also, one way of easiest way of looking at that is, this is the curve or surface what we have. First construct a point, in that normal to that direction, draw a circle with one particular radius. Wherever that surface is a tangential point, pick it. Something like, we have a point here, with an offset distance as radius, draw a circle. Now, we are going to draw a tangent there. So, that means we have that point. So, now join those points, construct an offset surface. This is the easiest way one can really construct any offset. If we want to really improve the quality of that curve, we use specialized curves. There is other terminology also we use when we are constructing these 3D objects using softwares, which we call chamfer. Chamfer is basically removing material on a plane. We do not round it off, but we straight away chop or remove that material like a plane, a cut. For example, if we are looking it in the planar view, let us consider this is the object what we have in 2 dimension. We want to really remove that material, cut, remove the extra remaining material. If we do that, we call that one as chamfer. No, we want to round it off, then we call fillet. For example, here let us look at for architecture point of view. Near Taj Mahal there is an entrance gate, the Great Tower. If we are looking at these columns, these are not rounded kind of column towers. These are something like a plate, next plate attached with another plate. That kind of sharp cuts, if we have it on that, we call chamfering. Chamfering always be a nice cut we will be having. Because of architectural point of view, you might be going to have that kind of thing. You want to stick some kind of pictures on the chamfer surfaces. So, you require flat surface rather than a curved surface. Then you go with that chamfering. So, in the next class, we will learn about SolidWorks and practice couple of examples how to use that tool. Thank you very much.